So yesterday, this is where we left off. Okay, we were working on this law of conservation of energy stuff, and we finished off yesterday by talking about the 60 kilogram athlete here, okay, and being able to calculate what their initial vertical speed was. Obviously not fast enough to get here on time, but okay, number 7 is the one I want to start on today. The 3.3 kilogram billiard ball, okay, propelled from the table at a horizontal speed of 1.5 meters per second. Okay, the table's 1.3 above the floor. What's the mechanical energy of the ball the instant it leaves the table? All right, so remember, to do this one, you need to remember the mechanical energy formula. All right, EM equals, okay, EK plus EP. All right, and remembering that those formulas, okay, EK is 1/2 mv squared, and EP is m times g times h. All right, I want you to start out with that one. Okay, I'll give you a few minutes on that, and then we'll go over it together. Okay, we'll look at a few of these other ones, and then we're going to move into sort of more difficult, higher level kind of questions. Yes? So for number 7, okay, if I'm looking for the mechanical energy, and I have the formula for each of these two, I got to look at what else I'm given. I know the speed, so I can find EK because I also know the mass, and I'm given the height above the table, right? So I should be able to find how much mechanical energy it has simply by plugging in my numbers, right? So 1/2 times the mass, which was 0.3, times the speed, which was 1.5 squared, plus 0.3 times 9.81, so m times g times h, 1.3 meters. Right? And when I plug all that in, I should get 4.16 joules. Everybody with me on that? Caroline? It does not. You can do the potential first and the kinetic second. Makes absolutely no difference. Okay. Now, looking at this one here with the pendulum. Okay, so the pendulum swings back and forth like so. All right, so let's say, just for argument's sake, it goes to here and to here. All right, as sort of its maximum positions. Where does it have the most gravitational potential energy? Where in its arc that it swings in does it have the most gravitational potential energy? Okay, yeah, if it went all the way to 90 degrees, yes, but we're saying it only goes to here, so it would be here. Yeah, as far as it can get, or as high above the lowest position as it can get, that's where it has the most potential energy, because there it has its biggest height, and it's also not moving. It has a speed of 0 at those points. Okay, where's the maximum kinetic energy? In other words, where is it going to move the fastest? Tom? In the middle, right? That's its lowest point. If this is its highest point, when it gets to here and turns around and starts falling back down, it's accelerating this whole time. It would be logical to assume it's going to be going its fastest at the lowest point. And since it can't fall any lower, it doesn't have any potential energy there either. All right? And then maximum mechanical energy, that's always the trick question. That is everywhere. Okay? Has the same amount of mechanical energy everywhere. Okay. Yeah, we're going to skip over those. We've kind of talked about those already. All right. So what I want to look at here is an example like this. Okay, I've got this roller coaster. All right, and I'm going to assume that this roller coaster exists in the perfect physical world where there's no friction, there's no air resistance, there's nothing to sort of slow it down. All energy is conserved in this place that is imaginary. Okay, but it has a mass of 1,600 kilograms, and at the top of the first hill, which is 50 meters higher than its lowest point, okay, it is moving at 5 meters per second. I want to find out how fast it's going over here when it is only 8 meters off the ground. All right, now this is a law of conservation of energy question. Okay, its initial mechanical energy is the same as the final. Right, so the amount of mechanical energy it has when it's 50 meters above the ground is the same as the mechanical energy it has here at its final position. All right, I'm going to give you a couple minutes and see if you can find a way to figure that one out before I solve it for you. Okay, as I think there's a few of you that'll get this one right off the bat. Okay, give you a couple minutes on that one. Okay, the other hint I'm going to give you. Remember, we calculate mechanical energy by adding potential and kinetic. Okay, there's my little hint. You know the formulas for these. Okay, so let's have a look at this. I had a question just like this on last year's unit and final exams. Okay, so be aware. Expect something this level of difficulty by then. Okay. The energy I have here is the same as the mechanical energy I have here. It's just there's different amounts of potential and kinetic in those two positions. So what I want to do first is decide where is VF. VF is part of kinetic energy final. Right? So it's part of that term there. I'm going to need that term by itself. So how do I get EKF by itself right now? If I'm adding EPF to EKF and I want to get EKF by itself, what do I do with this? Right, move it to the other side. Move this to the other side by doing what? Subtracting it. All right, so that's my first move. Now I have EPI plus EKI minus EPF equals EKF. Now we've done a calculation kind of like this before when they were saying here's the mechanical energy and here's the potential energy, calculate the kinetic. That's what we did. All right, we just didn't have to do this first part before. All right, now I've got that. Now I'm going to put in all of the variables. So it's going to look like this. It's going to spread out a little bit. M times G times the initial height plus 1/2 times MV initial squared. So here's my initial potential. All right, so that'll be the 1600 times 9.81 times 50. Right, plus the initial kinetic energy. It is moving at 5 meters per second, so I'll have the 1/2 times 1600 times 5 squared minus m times g times h final. So 1600 times 9.81 times 8. And that's going to equal 1/2 mvf squared. I want to find VF. I still have to move a couple things. I need to move the half and the m. How do I move them over? Divide. All right, so what I end up with is m times g times hi plus 1/2 mvi squared minus m times g times hf over 1/2 of m equals vf squared. Do I want vf to be squared? Okay, so how do I get rid of a square? Square root. Okay, I know it's a lot of algebra. This is probably the most involved algebra you will do in this course, is this type of calculation. Okay, now I just need to plug in my numbers. All right. Now, mass is in every single term. What can I do with it? I can cancel it. Okay, if you're comfortable with that. If you're not, leave it in there. Put 1600 in for it every time. You're going to get exactly the same answer. All right? I think we talked about this the other day, right? I told you how I messed with people on that test. Okay, all right. You can leave it in. It doesn't matter. I like to cancel it because I hate having lots and lots of numbers. Okay, but I'll leave it in for this first one. So I'll have 1600 times 9.81. Okay, so I'm doing this term right here times 50, the initial height. Okay, I'm adding that to the initial kinetic energy. Okay, that was the initial speed there, 5 squared. Then I'm going to subtract, okay, mghf. So that's going to be 1600 times 9.81 times the final height, which was 8. And then all of that's going to go over 1/2 times 1600. Okay, now punching this into the calculator, you got two choices. Use lots and lots of brackets, or do it piece by piece. Okay, I'm going to show you how it works piece by piece because that's probably easier to see. All right, so 1600 times 9.81 times 50. So there's my initial potential energy, 784,800 joules. Add that to the initial kinetic energy, 0.5 times 1600 times 5 squared. All right, there is my total mechanical energy. I've added potential and kinetic together. All right, that's the mechanical energy anywhere on this one. Now, the next thing I have to do is subtract the final potential energy. Right? So to do that, I go subtract 1600 times 9.81 times 8. All right. There's my final kinetic energy. I want to find VF. So now I'm going to divide by 1/2 of 1600. All right, that's VF squared. I want it not squared. So there's the final speed of the roller coaster. 29.1 meters per second. Okay, you will be doing these by the end of the unit and you won't have any problem. Because here's the good news. They're all the same. All right, every conservation of energy question sets up just like this one does. Okay, it starts out with this, EI equals EF. The next step, here's the kinds of energy. Sometimes you'll be lucky and you'll be able to cross some of these off because they won't exist. Like for example, if this question didn't occur here where it was 8 meters off the ground, if it occurred here where it was 0 meters off the ground, there wouldn't have been any final potential energy, would there? Okay, and you'd be able to cross that off, and then you have a little bit less to do. Okay, but essentially they all set up like this. Okay, I move things over, I plug in my formulas, move whatever else I've got to move, put the numbers in, and calculate. All right, but they always set up the same way. Okay, so once you know how to do one, you essentially know how to do them all. Okay, everybody with me there? All right, if you're taking Physics 20, we do this again. Okay, in Physics 20, it goes a little bit deeper, but essentially we do this again. All right, and by the time people are in Physics 20, they're like, I remember that roller coaster stuff, Code, leave me alone with that. I know how to do it. It's easy. Okay. We typically go to West Ed for Physics 20 trip. Yeah. Okay. All right, is that making some sense? Now, I think I'll give you guys the sheet here on this and have you try a couple of the ones on the sheet. All right, sorry guys, it took me a while to find the file I had here. Okay, so what's on this worksheet is basically a few things, because I want to build up. I don't want to start out with those roller coaster questions, okay, because we haven't had a lot of time to kind of process that stuff. So what I want to do is, first off, there's 5 questions on work, okay, work energy theorem and work, okay, want to go over those. Then there's a few on using m times g times h, okay, gravitational potential energy. Some of those will also relate back to force times distance. Same thing for the kinetic energy ones here, okay, between 9 and 13, there's some work energy theorem and 1/2 mv squared kind of stuff like we've been doing. Okay, and then the last section there is conservation of mechanical energy, and that is, okay, the stuff that we've been doing, and that's going to be like the roller coasters, the pole vaulter here, that kind of thing. All right, so that's where we're headed to. That's what I want to work on today, make sure that we get through that, and then tomorrow we'll work on this a little bit more, and then next week we're going to do a lab on conversions of energy. You'll have a review day for your unit exam. I'm thinking on Wednesday. Yeah, so Monday we'll do the energy lab. Tuesday we'll go over the last thing in this unit, which is efficiency. Wednesday we'll do the unit exam review. Thursday we'll have another day to talk about conservation of energy and work and energy and that kind of stuff to just make sure we understand it. Friday you'll start the next unit. And then June 2nd, the Monday, is your unit exam. All right, so it's coming right up. Okay, but we got kind of next week to work with this kind of stuff. All right, now I still haven't had a whole lot of people coming in and seeing me for help in scheduled helper at lunch, and some of you need to. I'm not going to point fingers, okay, but some of you need to come in and see me because I've been looking at the quiz scores and they haven't been going so well. Okay, everybody with me there? Now, that's the other thing we haven't done yet today is the quiz, okay? But I want to give you a little bit of time to work on this first since it's kind of the same stuff that's on the quiz, and I want to let you kind of get that through your brain before I give you that quiz 13. All right? Everybody follow? All right, so we're going to be writing the quiz in about 20 minutes. Okay? All right. Okay, guys, so just before we get to the quiz here, for number 7 with the shot putter, there's 2 different parts to this question. For some reason, I don't have both answers there. I just, for some reason, don't have them there. So we want to find the work done by gravity when the shot reaches 2.13 meters. Well, have you had to do work against gravity right from ground level if you're throwing a shot put? Yes, you have to pick it up. right? First you pick it up and bring it to 1.52 meters, and then you throw it up to 2.13 meters. You're doing work against gravity the whole time. So this number here, this 151.4, is the answer to number 1, the work done by gravity in reaching 2.13 meters. All right. Part B says determine the change in potential energy. Well, that means from between 1.52 and 2.13. All right. So in that case, then you're going to do an m times g times h calculation, right? Where h is the change in height between this and this. All right, so you go 2.13 minus 1.52, right? And you put that in for h, and I think you get about 43.4 joules or something like that. Okay? Everybody with me on that one? So it's just, I don't have an answer on there, and that's why people are getting confused. Like, I'm not getting that answer for A. Yeah, you're not, because you won't get it until you do B. Or sorry, you're getting that answer for A and a different answer for B. That's not the answer for B. Okay? This is the answer for A, and I think it's around 43.4, okay, for B. Everybody with me on that? All right, take out your quiz materials. Okay? And there's your quiz. All right, so for question number 1, you can give them first a mark for their givens, things we were told, the mass of the rock, the speed of the rock, okay? We were also told the initial velocity indirectly, okay? And that the catapult was brought backwards 3 meters, right? Obviously, work is being done because the kinetic energy of the rock is going to change as a result of the force acting on it from the catapult, okay? The reason the catapult has energy and the ability to do work is because whoever was cranking it down did work on it. All right. So we have work as a change in energy. Give them a mark for that. Okay. And then give them a mark for force times distance equals 1/2 mvf squared. Obviously, there was no initial kinetic energy because the rock was stationary while sitting in the catapult. All right. So if I want to find force, I divide both sides by d. Okay, and I'm left with this. F equals 1/2 mvf squared over d, or 1/2 of 50 times 29 squared over 3 meters. Give them a mark if they had something that looks like that. All right, and what we should find is that takes 7,008.3 newtons of force. Okay. No, this is force. Force is in newtons. Energy is in joules. Okay, work is in joules. But we didn't find either of those this time. We found force. Okay. All right. Make sure they have newtons as their units there, guys. If they don't, the answer isn't right. Okay. The units have to be in newtons. All right. Any other questions on number 1? Okay. For number 2, we're trying to find the height of a rocket. Okay. If a force of 200 newtons is exerted on it over a force of 4.5 meters. This would be like one of those bottle rocket kind of things like you would have made maybe in junior high. You know, you put the vinegar and baking soda in the 2-liter pop bottle. Okay, put a little cone on the top, and then it kind of just blows the top off and flies up in the air a little ways. Something like that. Okay, so what we've got here is we know the force, we know the mass, and we know the distance over which the force is exerted. What kind of energy about the rocket is it going to change? Potential. I mean, it's going to change the kinetic as well initially, but we're only worried about the maximum height where it only has potential energy. So, okay, that's the one we're kind of focused on. So give them a mark for their givens. Give them a mark for identifying it as a work energy theorem question. Work is a change in energy. Okay. We know initially it's on the ground, or at least we assume that. So our initial potential energy is 0. So we can cross it off. That leaves us with force times distance equals m times g times hf. So, if I want to get the final height, please not right now, we divide sides by m times g. Everybody with me? Okay. So we plug in our number. So give them a mark. Okay. Times 4.5 divided by 0.25 times 9.81. 57 meters.